Again, why I'm making this video is not because of this problem as a whole, but mostly because there's some difficulty in finding the phase constant when looking at the displacement equation for part B. So for part A, we're just going to go ahead and fly by it like a breeze, but then for part B, we'll take a little bit more consideration on this. So looking at all of what's given, we're given a left-hand end of a horizontal stretched cord oscillating at a frequency of 250 hertz at an amplitude of 0.026 meters. You got the force of tension acting on the cord to be 140 newtons, and the linear density, so that's just the density in a linear sense, not a volumetric density, it's going to be 0.12 kilograms per meter. The initial condition is that at t equals 0, the left end of the cord is going to have an upward displacement of 1.6 centimeters or 0.016 centimeters. And we want to add one more thing, the fact that it's falling. So V naught is going to be a negative. So that's going to help us later on. Now for part A, you want to know the wavelength of the wave produced. So there's a few functions for wavelength, but I'm going to see one just right off the bat that might help. What we can do is we can use the fact that velocity is frequency times wavelength. So wavelength is the velocity of a wave divided by its frequency. So since we want to find wavelength, we box it. We know what f is, but we don't know what f is. So automatically there's going to be a little bit of a side quest there. However, the side quest is kind of easy because it was just learned in lecture. V is going to be the force of the tension acting on the cord divided by the density. It could either be linear or volumetric, and in this case, linear. So we go ahead and use that equation. We plug it in for V, and we divide it by F to get lambda. So now lambda is going to equal to the square root of the tension force divided by mu over F. That's going to end up being 140 newtons divided by 0.112 kilograms or 0.12 kilograms per meter divided by 250 hertz. So lambda ends up being 0.1366 meters. That's the wavelength of the string as it's oscillating or as the wave travels through the cord. Now for part B, all we're really doing is looking at the displacement equation right here. That's D equals A sine kx minus omega t plus phi naught. And we're just trying to fill in everything we can, save for x and t, because those are both variable parameters. So we go ahead and look at our known list and plug in what we do know. A is 0.026 meters. K is, K is something that's interesting. Well, so what we do know from K is that the square root of force of tension over mu, so that's the velocity, is equal to omega over K. Okay, because these are both equal to the velocity function. So what you do is that you just link the two together. So we find K using the fact that we know, we know velocity now, but we also know this from the get-go. Omega is given as 2 pi f. So if you know what f is, you know what omega is. That's going to be 2 pi f. And lastly, we don't know what phi is, but we do have some information that could help us. And that is d naught is 0.016 meters upward bound. Okay, so we're using that initial condition given to us in the problem to find phi. We use 2 pi f to find omega. We use the relationship that relates to one another and velocity to find k. And we know we're used given to find a. So let's go ahead and find each of these one at a time. So A, all I'm going to do is just kind of affirm that we know it. K is going to be omega divided by this, or if you want to invert it, it's omega divided by the inverse right there. And that's going to end up being, if you plug in all the numbers, it's going to be 46 1 over meter. That's the unit for the spring constant, or sorry, the wave constant, not the spring constant, the wave constant K. So it's going to be 1 over meter. Omega is going to be 1,570 hertz. That's just 2 pi times 250. And it looks like we got everything except phi. And this is where the hard part comes in. Well, I think of it as a hard part. So what we're going to do is we're going to look at the same equation. Okay, so we're going to go ahead and write down the same equation, but for D naught, when t is equal to 0 and when x is equal to 0. So when they say D naught, they're talking about, it says at t equals 0, the end of the cord has an upward displacement of such and is falling. So that means that x is equal to 0 because it's the end of the cord, and t is equal to 0 because it's the beginning of the problem. So we write down the same equation here, except we know since x and t are 0, they cancel out, leaving phi naught in the argument for sine. Again, that's pretty awesome for us because then we can solve for phi naught using the inverse sine of d naught over a, which we well know what it is. That's going to equal to inverse sine of 0.016 meters divided by 0.026 meters. And that's going to give us two answers. First answer is going to be 0.663 radians. And the second answer is going to be 2.48 radians. Now, these are the two values of phi that can make this happen. The way you can find this out is by looking at the fact that we know that D naught is a positive value. So in a unit circle, so let me just kind of show you why I chose these two. Because if you plug this into the calculator, you're only going to get this. How do you get that? So we're going to look at a unit circle. We know since it's a sine function, we really just care about the y-axis of the unit circle. Okay. It's a positive, so we're looking at this part right here. Now, the first value you're going to get is 600 or 0.663 ratings, and we're just going to put it right up here somewhere. So the other value that can possibly make D naught, which is the y-axis of this unit circle, equal to a positive number is if we find some angle in which it's at the same height in the y value, right? Or in the y-axis of this unit circle. So since we need two solutions in which this D naught is at the same y value, we need to find not only this angle, but we also need to find this angle right here. I could have drawn that better, but basically the angle starting from the 0 point. And that angle is given by taking this right here, okay? And essentially just saying pi, which the pi is the 180 degrees, that's going to be this angle here, minus that first phi naught, this right here. You see that? So if I take pi minus this, and there's that symmetry there, here is the same as that, then we see that we're going to get another angle here. So pi minus that is equal to that second angle. And that ends up being 2.48 radians. Now, the last part, we're going to just look at it in terms of our logic. We know that not only does D have to be positive, but it will have to be going upward. So out of our two options here, and we have a sign here, we have two options. We have this or we have that. Now, in a unit circle, which is simulated here in the displacement function, it goes like this in a circle. So that means that the y-axis first goes up and then down, and then up and then down. So if the displacement initially is a positive and going up, oh, I'm sorry, it's not going up, it's falling. So aside from this mistake, if we have a displacement that is positive and going down, we know it can't be this particular angle here because this is up. This is a positive value and is going up in the unit circle as we're going in a circle like that. So the only possible option is the second option where it's positive and it's going down. And that's how the unit circle works. It goes counterclockwise, up and down, up and down. And so the y value is going to go up and down, up and down. In this case, it's going up and then back down here, this being the answer. So just with a little bit of sleuthing, we find out that that has to be the particular phase shift or phase angle. So now kind of going back over here because of room issues, we have D with respect to x and t is going to equal to 0.026 sine 46x minus 1570t plus 2.48. And that's going to be our value of the displacement function.